Good day, everyone. Today I'll be presenting our work titled Integrating Multi-Sensor Remote Sensing and Machine Learning Techniques for Flood Susceptibility Mapping in Lower Niger Delta in Nigeria. My name is Kehinde Opara, and I'm here from Nigeria, and I'm joined by my co-authors Ayebawanaemi, Winston, Paaru, Olasuodo, Inearrow, Ogidi, Oyinkuro, Emmanuel, Kalama, Buka, Jonah, Jonah, Ibiene, Joshua, Sampson, Owei, Doutimiyerin. Thank you as you listen. I would like to talk about the problem statements. What I mean by that is like the main challenges we want to address, like what we are addressing, the main challenges we are trying to address is one, recurrent severe flooding in the Niger Delta area. Number two is rapid urban expansion, increasing people exposure. Like how we want to expose people to other places, so they can live the area. Very limited ground-based ideological data and the urgent need for a better integrated geos- geospatial early warning systems. All these things are what we are um, addressing, or we are trying to address. As you can see in this slide, these are the images of flood area in that region. You see, can you see? We use a drone networking, a drone system to identify the areas. We identify the areas. You can see how deep the flood are. The flood is through across all region. And imagine what children are going through here. Imagine what a newborn baby that was born in this period goes through when this particular flood takes place here. So yeah, so this place is around the Obakata community, around Ogba, Egbeme, and Ndoni local government area in the year 2026. So and in Ibiene, Akinima, and Enajua area also. So this around the other West local governments. Also in 2024, this drone we used here was able to like capture the flooding event that took place there. Um, uh, Talking about the land use charge, the land use charge, 1975 to 2023. Um, as you can see in the image, you see the dramatic change over nearly 50 years. Water body increased by 76%, expanding the flood zones. You know, in, built up areas exploded by 1,000 plus percent. So more impervious surfaces, faster runoff. Cropland dropped by 90% and vegetation by minus 1.4%. Loss of natural floods, buffers. So I'm saying like the wetlands and the mangroves. Rangeland increased massively by 1,820% due to vegetation degradation. So talking about the extent of the flood, using the Sentinel-1 SAR data, so we are able to map this, using this Sentinel-1 SAR data by on a monthly basis. We're able to map the flood, the extent of the flood. So around October 2022, around 2022, October had the highest flood peaks, reaching around 350 square kilometer. So the said area, 350 square kilometer. As you can see, that is the amount of floods, how many people have been affected around that time. It was so enormous and crazy. You see the number of people affected with the amount. So it was the peak at that time. It was the peak. September was also high, especially around 2018 and 2022. August had the lowest flood extent, around 135 to 170 square kilometer. 2022 was the most severe flood, where it almost took over all the places. You know, uh, it was mostly driven by monsoon peaks and dam releases. Um, you know, all those hotspots include the Aga, Mbede, and Obricom area. These people they were devastated, and I don't know, they had to relocate themselves to other places. It was so severe. The hotspot zone, many people died because it was so chaotic. So using the data, we're able to, get the extent of how the flood almost wiped out a whole three community in that local government area. So correlation of upstream and downstream ultimately water levels in Nigeria. A strong positive correlation between upstream and downstream water levels. So the strong positive correlation between upstream, like around the upstream part of Nigeria, meaning all those local jar area, and the downstream level. Downstream peaks lag 1 to 2 months behind upstream measurements. This creates like a valuable early warning sign. So because it lags, so the lagging between 1 to 2 months behind upstream measurement. So this creates like early early warning windows for people to relocate to other places and also find alternatives for themselves. Seasonal water level pattern are synchronized across both locations. So the location between the upstream and the downstream, so the level patterns is synchronized. So it also enables 1 to 2 months early warning windows. Like I've said before, for the Niger data flood prediction. So because the upstream and the downstream are synchronized, so predicting the flood early is very important based on the data that is being derived from those synchronization. A strong correlation with SAR derived flood area. So of course, so this is what I just said. So based on the data that is being derived, so we can easily predict what the amount of flood that will be coming. So we can prompt people on how to go about it. So we have tested so many machine learning models, ML models, for flood susceptibility mapping. So as you can see on the slides, showing random forest, the accuracy was 0.9, AUC 0.991 for the accuracy for random forest. AUC is 0.93. So GBM accuracy is 0.88. SVM accuracy is 0.85. RF identified as the most robust classifier. So we're able to classify the random forest as the most robust because it came back with the most accurate mapping for what we are trying to do. So it came back with the most accurate mapping. That is why we're able to get this data here. As you can see in the slide, the graphs and the accuracy and the what's it called, and the data and the mapping data that we got. So yeah. So these are the dynamics of the integrated flood. Flooding results from compound drivers, rainfall, dam releases, land use charge, Again, black water effects make flooding last longer. Urban encroachment make it worse. The system behaves like a semi-closed hydraulic cell. So yeah. So based on our findings, we recommended that nationwide satellite-based flood monitoring. So we can have a flood monitoring system whereby we get details around to collect those data. Better coordination of dam release schedules, strict land use plan in flood plans, stronger early warning system, and community preparedness. So if you have some early warning system that we can notify the populace, around the area, to notify them early. So after we have collected the data for us to know when the flood is about to take place, so we can easily warn the people so they can find or relocate to other areas. The last one is building national capacity in AI-based ideology, whereby you can get the data and the building that system that can divert floods to other places that won't be affecting the human life. So and in conclusion, an integrated geospatial machine learning approach works very well. It's very effective. So also it delivers reliable flood risk mapping. So it delivers reliable flood risk mapping, supports SDG 13 climate action and SDG 11 sustainable cities. The framework can be applied to other data scarce river basins also. So these are the conclusions that was made. Above are the references that we use, in the course of all this. Leaning Wyhen, Yun, SN, Bajwaj, A, and Hill, AM 2019, urban flood detection with Sentinel-1, multi-temporal SAA observation, invasion framework remote sensing. So these are the reference that we use. So we make reference of all this. The Ogun, Koya, OO, and Olayiwola A, HA 2022. Them operation local rainfall and settlement growth pattern in the Niger data area. So from this reference, we're able to do everything that was done. Thank you for your attention. If there's any question, you can send it across. Thank you very much.